Pi is often introduced to us as a simple geometric tool, a ubiquitous factor hiding in high school geometry problems, dictating the circumference and area of a circle. But as the author Robert Kanigal noted, pi is not merely a tool for circles. It is a fundamental constant stitched across the entire tapestry of higher mathematics, from probability to infinite series. To understand how deeply pi is woven into the fabric of logic, it is wise to step back and look from a pure geometric perspective. Consider a circle embedded with a square. By comparing the area of the circle to the area of the upper right square quadrant, we find a perfect unyielding ratio. This is pure geometry, no approximation. But what if we reframe this certainty as a game of chance? Imagine choosing a random coordinate, point B, somewhere inside this unit square. What is the probability that this random point lands inside the quarter circle? If we begin scattering random points, we are essentially throwing darts at the board. As the dots accumulate, we can simply count them. We track the number of points that land inside the boundary compared to the total number of points thrown. Because of the law of large numbers, probability becomes geometry. The ratio of inside points to total points perfectly mirrors the ratio of their areas. By multiplying this ratio by 4, we can mathematically approximate pi. As our sample size approaches infinity, our approximation converges into an exact truth. We can see this in action computationally. By writing a few lines of Python, we can simulate millions of random points in an instant. This is known as a Monte Carlo simulation. With random numbers, basic logic, and the raw power of computation, the elegance of pi emerges directly out of the chaos.